So we've been looking at elementary matrices. So in the first video, we said there are three different types of elementary matrices. One's called a permutation matrix. Another one's called a scaling matrix. And the last one is called the replacement matrix. And we saw in the second video that if I take a permutation matrix and multiply on the left side of a matrix A, a square matrix A, it's going to swap out the rows, the ith and the jth rows of A. For the scaling matrix, if we multiply on the left side of a square matrix A, it's going to scale the ith row of A by a constant r. And the third situation, if I take a replacement matrix Rij of little r, and multiply it on the left side of a matrix A that's square, then the outcome is that A's ith row is going to be replaced with the ith row of A plus the r times the jth row of A. Yeah, so the ith row of A is replaced with the ith row of A plus r times the jth row of A. So basically, performing the elementary row operations that we've done since the beginning of the semester. Remember way back at the beginning of the semester when we started solving systems of equations? Reducing matrices, remember reducing matrices? We've been doing these three row operations the whole time. We've been doing swapping rows, multiplying rows by constants, and doing this whole replacement thing where we multiply by a constant and add it to a row to update a row, right? To replace a row. So this can all be accomplished by elementary matrices. That's pretty powerful. Now you can take this matrix and multiply on the left side by an elementary matrix, and you get your row, your elementary row operation. So very powerful. Okay, so we're going to talk more about elementary matrices. So it turns out that every elementary matrix is invertible, right? We've been talking about invertible matrices in this section 2.2. We've taken a little detour, it looks like, with elementary matrices, but it turns out they're very, very, very important when it comes to invertibility, whether or not a matrix has inverses. It turns out all elementary matrices have inverses. So that's what we want to state. Each elementary matrix is invertible. In particular, number one, if I look at the inverse of Pij, that's going to be Pij. Pij is its own inverse. Number two, if I look at the inverse of MIR, of course R is not 0 here, the inverse of that is going to be Mi 1 over R. And number three, if I look at the inverse of the replacement matrix Rij of R, the inverse of that guy is going to be Rij of minus R. Now I'm not going to prove this. We can do some examples, 3 by 3 examples. Let's say I'm talking about the first case, permutation. Let's say I got P12. So if P12's inverse is P12, that means we can multiply P12 with P12 to get to identity. Let's check that. So I take P12 times P12. I'll write it this way. P12 multiplied by P12. So what's P12? So you start off with the identity, right? And you swap the first and the second columns. So you're going to have what? 0, 1, 0, 1, 0, 0. Okay, so then you have that again. 0, 1, 0, 1, 0, 0, 0, 0, 1. Let's multiply these and see if we do, in fact, get the identity matrix, I3. I'll go purple. Okay, first row, first column. 0 plus 1 plus 0. Make some space. All right. First row, second column. 0 plus 0 plus 0. It's a dot product there. Okay, let's take the dot product of the first row with the third column. 0 plus 0 plus 0. Okay, first row done. Second row. Getting tired. Second row. First column. Dot product. 0 plus 0 plus 0. Second row, second column. We're going to have 1 plus 0 plus 0. Second row, third column. 0 plus 0 plus 0. All right, second row done. Third row, dot products. Ooh, crap. I lost something. It should be a 0. That should be a 0. All right, let's get back to the dot product of the third row with the first column. It's going to be 0 plus 0 plus 0. Third row with the second column. 0 plus 0 plus 0. And the third row with the third column. 0 plus 0 plus 1 times 1 is 1. All right, let's write that down. That's what? 1, 0, 0, 0, 1, 0, 0, 0, 1. Hey, that's the identity I3. Right? So that means that P12, its inverse is the dude we had to multiply it by to get I3. So the P12's inverse is P12. Right, that's what we expect. Okay, let's do another example. Let's do MIR inverse example. Okay, so let's look at M25. Its inverse should be M2 1/5 according to this theorem. Let's say if when we multiply these together we get the identity. Yay or nay? Hopefully yay. So the M25 is what? 1, 0, 0. And the second row is multiplied by 5, so you get 0, 5, 0, and then 0, 0, 1. And M2 1/5 is almost the same, right? You get 1, 0, 0, 0, 1/5, 0, 0, 0, 1. And then we start calculating that. First row, first column, dot product is 1 plus 0 plus 0. First row, second column, dot product is 0 plus 0 plus 0. First row, third column is 0 plus 0 plus 0. Now let's go to the second row. Dot product is going to be 0 plus 0 plus 0. Second row, second column. It's going to be 0 plus, we're going to do 5 times 1/5, right? 5 times 1/5 is 1, plus 0 times 0 is 0. So 0 plus 1 plus 0. All right, second row, third column. Dot product is 0 plus 0 plus 0. All right, second row done. How about going on to the third row? And dot producting the third row with different columns. Third row with the first column is 0 plus 0 plus 0. Third row with the second column is 0 plus 0 plus 0. And let's do the third row with the third column. 0 plus 0 plus 1. Put it all together. You get 1, 0, 0 on the first column, 0, 1, 0 on the second column, 0, 0, 1 on the third column. Hey, that's the identity, right? That's I3. Yeah. So that means we had to multiply M25 by something to get the identity. What do we have to multiply M25 by? It's inverse, right? M2 1/5. So because we had to multiply M25 by M2 1/5 to get the identity, that means M2 1/5 is the inverse of M25. M25's inverse is M2 1/5. Okay, pretty cool. As expected, right? As expected. That's what the theorem said. Okay. Now let's look at this last type, the Rij of R type. It's called the replacement R, 2, 3 of 5, let's say. So its inverse should be R2, 3 of -5. Let's see. So what's R2, 3 of 5? So you start off with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. In the 2, 3 spot, you're going to erase the second row, third column. You're going to put a 5. R2, 3, -5 is almost the same. You got 1, 0, 0, 0, 1, 0, 0, -5, 0. So rather than a 5, we have a -3. Now let's calculate this product, see if we get the identity. First row, first column, dot product is what? 1 plus 0 plus 0. First row dotted with the second column is 0 plus 0 plus 0. Ooh, crap, I lost something. Don't ever lose anything. First row, third column is what? 0 plus 0 plus 0. First row done. Second row, dot products. Second row, first column. Second row, first column. 0 plus 0 plus 0. Second row, second column. 0 plus 1 times 1 is 1 plus 0. Let's do second row, third column. Dot product. 0. Here we go. 0 times 0 is 0 plus 1 times -5 is -5 plus, here we go, 5 times 0 is 0. Did I do something wrong? Ooh, I wrote it down wrong. There's a problem here. There should be a 1 right there, right? I miswrote my matrix. There should be a 1. So that's going to change things a little bit, right? Let's do that one more time. One more time. That's what happens. You erase stuff. Okay, that was a 0. That was a 0. That was a 1. Okay, so we were doing the second row, third column entry. This is the interesting one. Dude, what did you do? Why did you do that? This is 0, that's a 0. Okay. Second row, third column. Let's be careful. 0 times 0 is 0. Plus 1 times -5 is -5. Plus 5 times 1 is 5. Aha! So we get a -5 and a +5. They're going to cancel out, right? They're going to cancel. They're going to go. All right, so that was the key. That was the most important entry right there. Why is it doing that? All right, now back to entries. Let's go on to the third row, first column. Dot product, 0 plus 0 plus 0. Third row, second column. 0 plus 0 plus 0. And, shoot. Don't do that to me, please. Don't do that. Dot product. Third row, third column, you're going to get 0 plus 0 plus 1. So in finality, you get 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the identity, I3. So what do we have to multiply R2, 3 of 5 by to get the identity R2, 3 of negative 5? That means R2, 3 of 5's inverse is R2,